Let's start chapter 7.4, which is about arc length, and in a later part it's about surface area of revolution. Here's a real thing that happened. My sister one day took a flight, and when she landed she called me and said, "That was the craziest flight ever." And I went and looked it up on Flight Tracker, and here's just the boring part of the flight. In a later chapter I'll show you the more interesting part. But let's just think about this boring part. I've got the Flight Tracker data here, so we know where her plane was at various time points. I don't remember which way it was going. I think it was going this way. So here's my question for today. What total distance did the plane fly during this boring part of the trip? So here's the data that goes into this graph, and write some of the arithmetic to demonstrate the calculation you would need to do to find the total distance that the plane flew during this part of the trip. You don't actually have to crunch all the numbers. If you really wanted to do it in a spreadsheet, I suppose you would. I wouldn't object. And then also think about what assumptions are we making in doing these calculations, and do you think those assumptions are reasonable or are they unreasonable? So pause the video and work on that. I'm going to switch to paper and pencil. All right, here's the essential part from the sheet before, our x and y coordinates. Here's one way to think about it. We were looking at a segmented flight, kind of like that. Could I compute the distance from here to there and the distance from there to there? That wouldn't be too bad, right? So I could say, what's the distance formula? Do you remember it involves kind of a right triangle like that, and thinking about the change in x and the change in y? So let's compute the change in x here. So just from this data point to that one, you could say it's 76 to 83. So 83 minus 76 is 7. And then do the same thing for y. 44.4 minus 43.3 is 1.1. The exact numbers, I know there was more decimals on the other sheet, but we're going for the main concept here. And then what's the distance flown on that one little flight segment from one dot to another? Well, we know this length and that length, and we want kind of the hypotenuse, so we're going to use the Pythagorean theorem, basically, right? So we could say the distance on this segment, and that would be the square root of 7 squared plus 1.1 squared. And then you do the same thing on the next row, the same thing on the next row, same thing on the next row, all the way down. And then what would be your total flight distance traveled? Well, once you get down here, you could add it all up, and this would give you your total distance traveled. That's one way to get the total distance traveled. A more interesting way is to have another column that's distance so far. You could say cumulative distance so far. On the first row, I would put a 0. When you're at this first point, how far have you flown ever since that first point? 0 distance. And then on the next row, you could say, take the previous row plus whatever distance we just flew from the first row to the next row, and then repeat that progressive summation. And then on the last box here, that would be your total answer so far, or your total distance. You wouldn't sum the column. This box would be equal to that box. So these two would be equal to each other, and we'd say do not sum this column, because it's already summing stuff from over there. So that would be a straightforward way to do the problem in a spreadsheet. What kind of assumptions are we making in this calculation, or you could say what things are we ignoring? Well, when I talked about this in class with students, some of them said the airplane's path is probably not exactly linear between points, and I agree with that. It's probably at least a little bit curved. So between our data points, do you think that's a reasonable assumption? Well, so we're imagining that it's straight lines. You could say, well, it probably curves a little bit. Can you tell that that's a little bit curved compared to that one? Is it plausible that the plane went woo, woo, like that? Well, what does it depend on? Depends on how close together the data points are. If they're 1 meter apart for an airplane, I'm pretty sure the airplane did not do this from 1 meter to the next. If they were 1,000 kilometers apart, it's possible that the airplane went, avoiding thunderstorms or whatever. So let's ask, is this reasonable? And it depends on how far apart the data points are, right? Another one, someone pointed out that we only had X and Y data, and this is an airplane. From what I've heard, they go up and down too. So we're ignoring altitude. We're pretending it's just a flat flight all at the same altitude, you could say. Is that a reasonable assumption? Well, if you look at the distances we're going here, just the first data point was 7 kilometers. Airplanes can only go like, I don't know, 7, 10 kilometers up. Maybe probably not even that. So it's flying here dozens and dozens of kilometers left and right, backward and forward, but it could really only be going a few kilometers up and down. So if we're ignoring that, but it's probably not very big anyway. So delta z would be pretty small. And then another one, if we want to get really fancy, we're presuming that an x, y, z coordinate system makes sense, that a rectangular x, y, z coordinate systems that is, that we're flying in kind of a flat mathematical plane rather than around a sphere. Last I heard, the Earth is a sphere. Is that reasonable? Well, this part of the flight was, again, only maybe a few hundred kilometers, so we weren't tracking it as it flew around a quarter of the globe or anything. So it's probably pretty reasonable. Unless it was a flight on a smaller globe like Mercury or something, but she didn't mention that. All right, so in the next video, we'll go turn all these ideas into math notation. I'm sure you can't wait.